morning, everybody, and welcome to IFCA. Today we have Oleg Lebedev, who was last week in the dark matter workshop we had in Saint Mark, organized by us, and he kindly accepted to come here to give a seminar given that he is in town on Higgs and cosmology. I will say only this, and after this, as you can see, the talk will be in English. The word is for him. Thank you, Oleg.
Okay. Thanks very much again. I'm very, very happy to be in this wonderful place. So this is my first time in Santander. So it's surprisingly nice. Jonathan gave me sort of a lot of confusing instructions, so I'm not really sure what I should do now. So he said that perhaps I should give some personal information, so I'll probably do that. Okay, so right. I was educated in Russia, in St. Petersburg. So that's where I did my bachelor's and master's degree. Then after that, I did my PhD in the U.S. at Virginia Tech. So I'm specializing in particle theory. So I was doing the minimal supersymmetric standard model, Higgs doublet models, and so on. So physics beyond the standard model. And then I continued with that, so I moved to the UK. I was a postdoc at Sussex, then DAISY Germany, CERN, and then I was again back to DAISY as a staff member, and now I'm professor at Helsinki. And most of the time I was doing quite sort of top-down physics, in the sense that you start with some beautiful model which could explain everything. And as you probably have noticed in the last couple of years, that this approach sort of seems like it has failed, or at least to a large extent. Because things that were expected at the pre-LHC stage turned out to be wrong, and we don't really know what to do with it. So basically a few years ago, I started doing more bottom-up physics, meaning that you basically take something which you pretty much know is there and try to explain it or try to find some interesting features. And so one of those things is the Higgs boson, which was discovered. We know it's there. On one hand, on the other hand, the Higgs sector poses lots of puzzles. Yeah, so this is really the least understood part of the standard model. There are tons of problems all over the place in the Higgs sector. So for instance, the hierarchy problem comes from the Higgs sector. The flavor problem comes from the Higgs sector, because we don't know why the color coupling, so the coupling to the of the Higgs to fermions, are so small. They exhibit a hierarchical pattern, so nobody knows where it comes from. Again, it's really just the Higgs sector. So if you go to the gauge sector, there are no problems, no puzzles. All the numbers you look at are order 1. There is even gauge coupling unification, so everything seems wonderful, right? But if you look at the Higgs sector, you find there are tons of problems. And so this is one issue. And the second thing is that in the Higgs sector, not much is actually measured, right? Apart from the Higgs mass, which is now precisely measured. But then the couplings to some heavy fermions are measured, and the couplings to vector bosons are measured. But for instance, the Higgs self-coupling has not been measured. And it could be quite different from what we expect in the standard model. So, and that is really important, because it can be, this coupling can be affected by new physics very easily and can change totally the fate of the universe. Okay, I will probably touch upon that later at the stage of my talk. So, so this is basically the reason why I got interested in the Higgs sector, because it has it has some interesting features. It can hide new physics. So it could be that new particles couple only to the Higgs, and no other particle of the standard model, and that perfectly fits all the data. I mean, you don't have to hide your particles, so it's just the way it happens. And the second problem, which got me interested in this business, is that in cosmology there are certain phenomena that certainly require physics beyond the standard model. So, for instance, dark matter is there, we know for sure, so we have to explain it in some way. Okay, and that perhaps could be done with the help of the Higgs sector. And finally, there is inflation, so nobody knows, again, how it proceeded. But again, I will try to argue that perhaps there is some relation to the Higgs factor. This is all still, well, some bits of what I'm going to talk about are speculative, but some others are pretty solid. So at least, you know, I can make certain statements which are true. At least I think so. All right, so shall we proceed now? Okay. Right, so the Higgs in cosmology, so I'll briefly cover 3 subjects. So I'll talk about the Higgs in the hidden sector, the Higgs in dark matter, and the Higgs in inflation. So I'm not sure how much time I have still, so we'll see. I'll try to be brief, maybe. If you're interested, you just ask questions. Right. So okay. Basically, this is the setup. The setup I'll be looking at. So there's no question about this bit. Yeah, we have the standard model. It works perfectly. The best fundamental theory we have in physics. There's really nothing better than that. Now, I also have the hidden sector here. Why? Well, because we basically need it from cosmology. Okay. I forget here about all the problems of particle physics, you know, strong CP problem, flavor problem, and everything else. But what I can say for sure is that there is dark matter, there is inflation. So, and those things are not happening within the standard model. So I have to add an extra sector. So that's the motivation for the hidden sector. And by hidden, I mean it's a collection of fields, particles, which have no quantum numbers under the standard model. So they have no hypercharge, no isospin, no color, no charge, nothing. They're just completely complete singlet states. For instance, one example would be a sterile neutrino. A sterile neutrino has no quantum numbers under the standard model. Now, and what I will assume is that the only connection between the two is provided by the Higgs boson. So the only particle of the standard model that can probe the hidden sector is the Higgs. I will explain why this is a reasonable assumption in a second. All right. So, but this is the setup you should bear in mind. Okay. So this setup goes by the name of the Higgs portal, which was coined by Wilczek, the Nobel Prize winner, about 10 years ago with his student. But already people in the 80s worked on the setup in a different context. So this framework is sort of pretty old. Now, okay, so given this assumption that the only particle that connects the two sectors, I can write down the lowest dimension operators that couple the Higgs to particles of the hidden sector. Now, suppose that in the hidden sector I have a single scalar, real scalar S. In that case, I can write down this interaction, which is gauge invariant, Lorentz invariant, and dimension 4. So it's renormalizable, so basically you just have to write it down unavoidably, right? So you cannot forbid it. If there are spin 1 particles in the hidden sector, I can write down the following dimension 4 operator, so h dagger h times the vector potential squared. Again, it is invariant under all symmetries. But it only exists if the vector has mass. So if the vector has non-zero mass, this operator does not violate gauge invariance, and it's there. Perhaps I can also mention how it's generated later on if I have time. And finally, if we have fermions in the hidden sector, I can write down this coupling, h dagger h, chi bar chi. Again, it's invariant under all symmetries, but the only difference now is that it's dimension 5, so this interaction has to be divided by some scale, so new physics scale. So all of these operators couple the hidden sector to the Higgs field. And these are the lowest order operators, so basically if you want to study physics of the hidden sector, so these would be the leading terms. Okay. All right, so what is so special about the Higgs? Why did I choose this specific setup? Okay, so the reason is that h dagger h is the only gauge and Lorentz invariant operator of dimension 2 that one can write down in the standard model. There is no other operator with that property. So that makes the Higgs very special. Given that, we can use the usual QFT logic and write down all renormalizable operators that include this quantity. And so then one finds that you can write down h dagger h, s squared, where s is the hidden scalar, just like on the previous transparency. And also, in general, you have a trilinear term where s, the s dependence is linear. In principle, it's also there. So these two terms would couple the hidden sector to the Higgs sector. And as I said before, this is unavoidable. It's very hard, or essentially within this framework, it's impossible to forbid terms of this type because they simply vary under all symmetries we know of. Now, let me assume for a second that this scalar in the hidden sector has some non-trivial transformation properties under some symmetry. So, for instance, I can invent a symmetry that reflects the sign of this field. So S goes to minus S. It's a Z2 symmetry. And if I impose this symmetry, this last term would be forbidden. And therefore, I just end up with the quartic interaction. Okay. So that is, for the moment, this is the only relevant term I will focus on. And in this case, S can constitute dark matter. Why? Well, the reason is that this interaction makes it stable because S couples to everything in pairs, so it cannot decay because each vertex contains two scalar particles. Okay, so decay is impossible. That can be reformulated in the language of symmetry. So, if you have S in the initial state, it has a minus parity under Z2. And if in the final state you just have standard model particles, they have Z2 plus 1 parity. So without violating this parity, you cannot let S decay into the standard model particles. Okay, it's the same argument. So it is stable. What is also interesting is that it couples very weakly to the standard model because all the interactions of dark matter would be mediated by the Higgs. And the Higgs couples very weakly to fermions. So, for instance, couples very weakly to light quarks, and therefore couples very weakly to nucleons, and that would suppress the direct detection signal for dark matter. So this is sort of a side benefit of this idea. Now, this is the case if so S is a nice dark matter candidate if it does not develop a vacuum expectation value. Okay, so if the vacuum expectation value is 0, this Z2 symmetry is unbroken, and I can have a nice dark matter candidate. Now let me assume for a second that S does develop a vacuum expectation value. In that case, it can mix with the Higgs. So what can we say about this system? So well, in this case, we have two scalars which mix with each other. Okay. So there are two mass eigenstates, and we know one of them is the normal Higgs because it's been discovered, its properties have been measured. So one of the eigenstates is the 125 GeV Higgs. And there is another mass eigenstate which is mostly singlet, but it has a small admixture of the Higgs field. Okay? And this system is characterized by the mixing angle that controls how much singlet is how much is the singleted mixture in this 125 GeV Higgs state. Okay, so the relevant constraints here come from electroweak precision data, LHC coupling measurements, even wave physics, lab, and so on. So there are lots of interesting constraints. So this is a summary of those constraints. On the horizontal axis, we have the mass of the second eigenstate. And on the vertical axis, we have the mixing angle, and all the colorful regions, except for the green one, are ruled out by various data. So the gray area is ruled out by electroweak precision data, so basically by very precise measurements of the W mass, with mixing angle, and so on. There is a very large list of observables which constrain the Higgs mixing with with another scalar. Then there is also a constraint from Leb that applies to this mass region, where you could, in principle, produce the second scalar eigenstate, but nobody has actually noticed any deviation from the standard model at Leb. Therefore, there are constraints. So, meaning that this mixing angle has to be smaller than about 0.2, 0.1. So everything in color is ruled out, right? So the white area is still allowed by data. So if the second eigenstate is light, then the mixing angle has to be small. And there is also non-trivial data from the LHC that constrain the existence of the heavy Higgs. So suppose this H2 is a heavy scalar, you would produce it at the LHC the same way you produce the Higgs, and there are constraints on that. So all of those things come from the LHC. There is also the yellow region, which comes from the coupling measurements, which constrains this sine theta independently of the H2 mass. So what is the bottom line here? Well, the bottom line here is that the white region is allowed, and this green one, I'm not going to talk about this, but the green region is also fine. The point is that if H2 is as heavy as, say, 300, 400 GeV and more, the mixing angle can be as large as 0.3, so something like that. You see 0.3 is here. And this mixing angle is very large. I mean, you would naively assume that things like that are ruled out by the data, but that's not true. So the mixing between the Higgs and the hidden sector can be as large as 0.3, which is almost order 1. Meaning that it is still not hopeless to look for deviations in the Higgs couplings. It's not hopeless to look for additional scalars at the LHC. So all of this is perfectly consistent with the known data. Okay, so this is my bottom line here. Now, but let me come back to my original model, in which S does not develop a vacuum expectation value, so it's perfectly stable. The Z2 symmetry is unbroken. In that case, the S field is my dark matter. So what happens in this case? Can I actually fit the data? And the answer is yes. So all the relevant diagrams are shown here. So dark matter annihilates into the standard model particles through the Higgs. So that controls the relic abundance of dark matter as measured by Planck and WMAP. Then the second diagram controls direct detection of dark matter. So again, this process is mediated by the Higgs because there is nothing else that dark matter couples to. And finally, there is a constraint from the LHC on the invisible Higgs decay. So this channel is open if dark matter is light enough. So if it's lighter than half the Higgs mass. In that case, you would have an invisible decay channel for the 125 GeV Higgs. So these are the main constraints. Now one can put them together and see whether there is any parameter space consistent with all the data we have. And the answer is yes. So this is not my plot. It's done by a relatively large collaboration of theorists, or mostly theorists, probably there are some experimentalists there as well, called Gambit. On the horizontal axis you have the dark matter mass, and in log units, log 10 units, and on the vertical axis you have the coupling between dark matter and the Higgs, again on the log scale. And the point is that the colorful regions, so the blue, green, yellow, are the regions preferred by the data. Okay, if you put all the information we have together, do a fit, and you find that you end up with this picture. So here there are three distinct regions. So one is the resonant annihilation region, which is very fine-tuned because you probably see it here. So you have to adjust the mass of dark matter to be exactly half the Higgs mass, which seems unnatural, but perhaps not impossible. But that appears very fine-tuned. And then there are two other substantial regions where no fine-tuning is required. One is at strong coupling. So in that case, the dark matter weighs about 100 GeV, and the self-coupling of dark matter, the coupling between the Higgs and dark matter is order a few, so it's not very small, so it sort of approaches the strong coupling limit up here. And then there is another region which is favored more, so it's at the TeV masses for the dark matter, and the coupling here doesn't have to be large, so it varies between 0.1 and say 1. So, but you see here that this region is preferred, and that sort of, if you forget about the fine-tuned resonant region and large coupling region, which is perhaps less questionable, and you focus on this region, you might conclude from this plot that in this simple framework, you are forced to have relatively heavy dark matter, because in this region you have multi-TeV dark matter. Okay, so perhaps it's not a problem, but now the natural question would be whether you can find other models within this framework which have a completely different behavior and allow for very light dark matter. So, and the answer is yes. So all one has to do is to replace this real scalar, 1 degree of freedom, with 2 degrees of freedom, so a complex scalar. So in that case, one writes down the following potential terms. So V0 contains all dimension 4 terms which preserve U1 global symmetry, which amounts to changing the phase of the S field. So this is my ad hoc assumption, so I introduce a complex scalar and I require my theory to be invariant under rephasing of this field. Okay, it's just a simplifying assumption. And so one ends up with this collection of terms, which have exactly the same structure as the potential terms in the previous model, where S is real. However, there's one feature here, and that is if S develops a vacuum expectation value, it breaks this global symmetry and leads to the existence of the Goldstone boson. And Goldstone bosons are massless and they're ruled out by the data, so we don't want that. For that reason, one needs to introduce a soft term which breaks this U1 symmetry explicitly. So all the details are unimportant here. If you don't understand, it doesn't really matter. So the point I'm trying to make here is that if you make this assumption, which seems rather minimal, you find that the measuring part of this S field plays the role of dark matter. So this measuring part of S is absolutely stable. So it has the same, exactly the same behavior as this S. Okay? And the model is essentially just as simple as the previous one. Now, what is interesting about it? Well, if you now calculate the